meetings, but this is mainly class. All right. So 6.5 gives us another way to calculate the area under the curve, which is the trapezoidal rule. And maybe this rule is going to be a better approximation just because of the shape of what a trapezoid is. So whenever I draw a curve, I tend to draw a curve that looks like that. I don't know why, it's just the way I draw them. Okay? So instead of making rectangles, which is what we made before, we're not going to do that anymore. Now what we're going to do is make trapezoids. And because trapezoids have that one edge that's tilted, they will fit better perhaps under our curve depending on what the curve is shaped like. And we'll talk in a minute about overestimating versus underestimating. So if, let's say, I draw my trapezoids from A to B, and I want to find the area under the curve from A to B, then I'm going to start by breaking that interval into a certain number of subintervals. And so I let my beginning be x0, this will be x1, x2, x3, bless you, holy cow, x4, and then I'm going to number my trapezoids, 1, 2, 3, 4. So, $1,000,000 question. What's the area of a trapezoid? Okay, so for my first trapezoid, it would be height over 2 times B1 plus B2. And as we start to use this to apply it to all of the subintervals, H is going to be the width of an individual subinterval. That's this part here is going to be H. And if we make all of our subintervals equal, which just makes sense, it's silly to have them be different widths, then I can say that H is going to be B minus A, which is my whole distance here, divided by my number of subintervals, which I'm going to call N. And of course, in this problem, it's 4, but I'm trying to come up with a general formula that I can use for the trapezoidal rule. And then, what's B1 going to be? Okay, it's going to be the left side. It's going to be this. It's the y value for x0, so I'm going to call it f of x0 because I'm going to assume, oh wait, my curve was blue, that this is f of x. And then what's B2 going to be? No, it's going to be f of x1 because it's going to be this side. Okay. And of course, as Casey alluded to, they're the y values, so I can call them y0 and y1 because they go with x0 and x1. see what we're doing here. Which means that I can rewrite my formula for T1 is going to be h over 2 times y0 plus y1. Yes? We good? We got it? Okay. So if that's what T1 is, what's T2 going to be for my second trapezoid up here? Yep. y1 plus y2. And then how about T3? And T4? Good. What do you notice here when we look at all four of those? They all have the same, yes, they do, because remember that the height is really the width here of my subinterval, and I've made them all equal. So yep, they all have the same height. What else do you notice? Well, if the h's are all the same, then I could add these all together and pull out h over 2, because that would be a common factor. And then what would I be left with? No, not quite, Sarah. I double count. We're getting there. It's probably the equation you read about. Okay, which is why it seems so familiar. But we double count the sides of the trapezoids that are on the inside. Okay? So we would actually get, I don't know if I ever actually have the formula here, but if I was going to write down the formula for the area that I get under the curve using the trapezoid, I end up writing b minus a over 2n, right? Because I had that 1/2 that was hanging out. And then I have y0 plus 2y1 plus 2y2 plus dot, 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 plus 2yn minus 1 plus yn. Okay, so every height, every base really, except for the first one and the last one, are doubled, which should be the formula that you had in the book. Okay. All right, we got it? So when we talk about any approximation, we talk about whether we're underestimating or overestimating. And for instance, we talked about that with LRAM and RRAM and MRAM. And we talked about that the rectangular approximation depended on whether the curve was increasing or decreasing, whether or not we were going to underestimate or overestimate. So let's talk about that now in terms of the trapezoid rule. So I'm going to really exaggerate my curve. And just to show you what I'm thinking about, I'm also going to make a really big subinterval, which of course I would never do. So let's just pretend that we're really zooming in here. Okay. So is my trapezoidal method going to overestimate or underestimate for a curve like this? Overestimate. And what kind of a curve is that? It may very well be, but that wasn't what I was going for. Okay. Yeah. Yeah, I mean, you could, but and if you think about it, it would work because B1 and B2 would be the same. So you'd end up with like 2B1, but you're going to divide it by 2, so you'd end up with B1 anyway times the height. All things end in rectangles, it seems. What kind of a curve is this, though? A general statement you can make about this curve. Yeah, but 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 this curve is positive too. It's what? Yes. Okay. So, and what's the calculus way of saying concave up? Is what? Okay, mnemonics are there for a reason. Okay, so if my curve is going to be concave up, my trapezoidal method is going to overestimate. If my curve looks like this, and again, I make a ridiculously large subinterval, now am I going to overestimate or underestimate? Okay, so the trapezoidal method underestimates for what kind of curve? And then yes, that means f double prime is less than 0 in this situation. Okay. So again, a nice thing about this estimation, about finding the area under the curve, is I don't necessarily need an equation, as if I were going to find the integral. I could take a table of values and apply this method, and it might give me a better estimation than LRAM or RRAM would. So let's see what that's about, and let's look at page 316, number 12. If somebody would read it for us, please. Thank you, Zach, because that was totally unnecessary, Priya. All right, so I don't know anything about this as an equation. Of course, I could try, but once again, it does not exactly look linear to me. And if it's not a straight line, I'm not really going to fit it. Priya, you need to take stuff out of your mouth before you talk in my class, okay? I don't know if it's exponential. This difference is 5, this difference is 8, this difference is 8, this difference is 8, this difference is 7. I don't know. Okay. But there is always something I know that relates speed, which is what I have, and distance, which is what I'm trying to find. Yeah. So let's back that up though a minute, okay, and start with this and get there. But you're right. Okay, so I can always say that speed or velocity is going to be equal to dx dt. And then this kind of brings us back again to differentials from chapter 5, because I can break the dx dt up and actually cross multiply so that I get v dt is equal to dx. And then by President's Day weekend, you're going to look at that and you're not going to be able to stop yourself. You're going to have to stick an integral sign in front of it. Just like my AP Physics students, you can't draw a free body diagram without writing down F net equals MA. Okay, you're just going to have to do it. It's just going to be a reaction. Okay, so what am I interested in here? What's my time interval that I'm interested in here? Yeah, but which seconds? We only know at this point in our lives how to deal with a definite integral. So I need limits on my integral here. 0 to 8. And I'm going to very importantly label it as seconds, because you should have noticed that my time is in seconds, but my speed is in miles per hour. And then I'm going to want it to be, my answer to be in feet, which is just another example of the stupidity of your book. Your book is stupid. But I did not choose it. So if I take the integral of x, what am I going to get? X, right? Okay. No, I may have misspoken. I did misspeak. I want to know what the integral of dx is. I probably said the integral of x, but Casey knew what I was asking, even though I didn't ask it correctly. So this is going to give me the position at 8 seconds minus the position at 0 seconds. And if we assume that we start at x equals 0, because why wouldn't you? I can set this equal to 0 just by saying my starting point is x equals 0. Okay. So this basically tells me that x of 8 seconds is going to be my integral from 0 to 8 seconds of v of t dt, which, as Casey told us a couple minutes ago, is the area under a v of t curve. Now the problem is I don't have an equation that goes with this data. I just have a bunch of data. I don't want to go through the problem of trying to fit the curve by hand, because like I said, I don't think it's a straight line. And honestly, if it's not a straight line, your chances of fitting it are pretty slim. So what am I going to do? I can find the area of subintervals using what? My trapezoidal rule, right? That's why I have it. I can't use LRAM, RRAM, or MRAM because, again, I don't have an equation to put into my calculator, although I could figure it out by hand. But one of the nice things about the trapezoidal rule is I don't have to worry about picking the left hand or the right hand or the middle for the height of my rectangle. It takes all of the data into account. And so I don't have to choose whether I'm going to overestimate or underestimate and not know. Okay, you with me, Sari? Okay, Zoe, you with me back there? All right. So my formula for my trapezoidal rule, which we wrote down before, is h over 2 y0 plus 2y1 plus 2y2 plus 2yn minus 1 plus yn. n is my number of subintervals, right? Sari, how many subintervals am I going to have? 8. Okay. And what's the height, h, of each of my subintervals going to be? b minus a over 2. No, 1, because b is 8, a is 0, and I'm going to divide it by 8. That's okay. So if I go back to my table, each of these intervals is 1 second, which is probably why Sari picked 8, because there are 8 seconds, and now each of those intervals is 1 second. But what we have to be careful about, though, is that our y values are going to be in what? What's the unit of our y values going to be? Miles per hour. Convert what now to what? I don't think converting it to miles per second is going to help. Maddie. Mm-hmm. Mm-hmm. So h is b minus a over n. So what's my upper limit on my table? What's the 8? What's my lowest limit on my table? How many subintervals do I have? So what's that equal to? When I wrote it here, if I substitute this in for h, then I do in fact get b minus a over 2n, but that's the same thing as writing h over 2. Okay, that's a good point to make. Okay. All right, so what I did, there are multiple ways to do it, is we need to convert this h into hours, is what I would do for starters. Okay. So how am I going to convert 1 second into hours? Okay, so 1 hour is 3,600 seconds, and what do we get? Is Priya right? You could, if you want to. But this isn't going to come out and be anything pretty anyway. Okay. So now what we're going to do is write this out. I'm not going to write out the whole thing, but h is going to be 2.78 times 10 to the minus 4 hours divided by 2. Y0 is our first value, which is 0, plus 2 times our second value, which is 3, plus 2 times, I did have it all written out, 7, plus 2 times 12, plus 2 times 17, plus 2 times 25, plus 2 times 33, plus 2 times 41, plus 48. And if we do all that math, what are we going to get? .0, what was it? And that's going to be miles, although that's not the same number of miles as I got. As if you got, okay. But we want our answer to be in feet. So anybody know how many feet are in a mile? Yep. What'd you get, Maggie? Oh, you didn't do it yet. Okay. 230. Really? No. No. So 238. I get 241. But what did you go all the way out to this decimal space? Oh, okay. Okay. Well, my answer was 241. They both rounded to 40. I'm not really worried about it. Yeah, that's the final answer. Nope, no more steps. Okay. It's, yeah, pretty dumb. All right, so we have another way of approximating things, which is Simpson's rule. And this one is a little more complicated, so that we end up with subintervals that are curved on top, which might help us better approximate our curves. So for Simpson's rule, we've got h over 3 is y0 plus 4y1 plus 2y2 plus 4y3 dot 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 plus 2yn minus 2 plus 4yn minus 1 plus yn. And h is the same as before, b minus a over n. Yep. So let's just try number 17 from the journal. I'm assuming that maybe we needed a little help with that one. Which just says, part A says to use Simpson's rule with n equals 4 to approximate the integral and then find the exact value to check. So our integral goes from 0 to 4 of radical x dx. It's probably going to be like a trapezoid with a curved top. I think there's a picture in the book. I find that when I do this, it's useful to make the x and y values, and as a matter of fact, I wouldn't even do it as a table. So for instance, what's x0 going to be equal to? Zero. And what's y0 going to be equal to then? 0, because this is my y, right? x1 is going to be, no, you can't graph it, Priya, and please, seriously. So y1 is going to be, if I substitute 1 into here, what do I get? 1. Right? If I have 4 subintervals, and my last one has to be my upper limit, what's x2 going to be? What's x3 going to be? Okay, so what's y2 going to be? There we go. And what's y3 going to be? And what's y4 going to be? Okay, and h is still equal to b minus a over n. 4 my upper limit, 0 my lower limit, 4 my number of subintervals, and that's going to give me 1. Okay. So you'll be able to look at that on your paper, but this tells me that S is equal to H, which is 1 over 3, and I have to go up to Y equals 4. So it's going to look like that. It may, yes, because it gets wacky. Okay. And then we said that y0 was 0, y1 was 1, y2 was radical 2, y3 was radical 3, and y4 was 2. And honestly, I would just pop it all into your calculator. Let's see what other people get. What'd you get it, Terry? What'd you get, Alf? Same? Okay. So then you can figure this out, because this one's pretty easy, right? It's really x to the 1/2 dx, right? It's radical x, x to the 1/2. If I take the antiderivative of x to the 1/2, what do I get? Over 3 over 2, from 0 to 4. And I can take my denominator, because it's a fraction, and flip it, right? And I get 4 to the 3/2 minus 0. And if you do that out, what do you get? $5.33, which is pretty close. It's not exact, but it's not going to be. It's an approximation. But certainly to the nearest tenth, they agree, right? Okay. On Monday, we will finish this section.